In this brief collection of videos, we are going to review the concept of linear approximation and walk through a couple examples. So here's our 1-minute summary or review of what we're doing when we're doing linear approximation and why it's useful. Pictured here, we've got this blue graph, which is the graph of some sort of function, y, which we're denoting by f of x. We've also got the tangent line to the function y is equal to f of x at some sort of fixed or specific input value a. So you can see that that straight line is tangent to the curve f of x because here's our input value a, and here's the point that lies both on the curve and on the tangent line. Now what we want to envision when we're working with linear approximation is that there's a small difference in x values, so the dx stands for difference in x values, between some sort of input a and some other sort of input a plus that difference in x values. So we're imagining we're very zoomed in on this picture. Now you'll notice that at a plus dx, the value of the function y is equal to f of x, and the value on the line, L of x, are actually different. But because we're very zoomed in this picture, they're not different by much. And so the concept of linear approximation is we are going to use the value that appears on this line to approximate the actual value of the function at a plus dx. And because a and a plus dx are not that far off, the difference between the actual value of the function and the approximation we get when we use the tangent line to compute this value instead of the function is not really that large. So with that short review, let's work an example. Let's find a decent decimal approximation for 1 over 97 without doing any kind of long division, but instead using linear approximations. So if our goal is to truly use a linear approximation, first of all we need that function y is equal to f of x, and it should have something to do with our problem. Here we're looking at 1 over something. We're just going to think about 97 as being some sort of value we want to approximate, and so we're going to use the function f of x is 1 over x. Next, we need a tangent line to the curve y is equal to f of x at some sort of specific a value. And ideally, we want that a value to be near the x value that we want to approximate. Since what we're trying to compute is 1 over 97, which represents f of the input value, 97, the a value that we're looking for should be sort of close to 97 and should be particularly nice when we plug it into the function f of x. So here, our a value should be some sort of number close to 97 where 1 over a is nice. We're going to choose to use a is equal to 100 because with our decimal system, looking at something like 1 over 100 is super easy. Once we have that specific a value, the next step is to compute the equation of that tangent line that we're calling L of x here at this specific value of a, where our a in this example is 100. So, in order to write the equation of a line, we always need two things. We need a point on that line, and we need the slope of the line. Now that we know our specific a value, and it was selected so that f of a was particularly nice and easy to compute, the point that's going to be on the line is 100, 1 over 100, or alternatively 100, comma, 0.01. Next up, we need to find the slope of the line, which we're going to find via the derivative of our function f of x, denoted f primed of x. Given that f of x is 1 over x, we're going to first rewrite f of x in exponential notation as x to the negative first power, and we can then compute the derivative of f of x using the power rule. Our derivative will become negative x to the negative second power, which we can rewrite in this manner over here. That's a general formula for the derivative of the function f of x. We're in particular concerned with the value of this derivative at our a value, which is 100. So plugging 100 into this derivative, we find that f primed of 100 is negative 1 over 100 squared, or alternatively, if you prefer decimals, negative 0.0001. Having the point on the line and the slope of the line, we can come up with the equation of the line using one of our many forms for the equation of a line, slope times x minus our a value plus our f of a value. If you're curious, you can see that equation of the line back in this picture as our slope times our x minus our a value. That's really the dx that we're computing, and then adding on to it our f of a value. Now we're almost done with this problem. So far, we have our function, we have our equation of the tangent line, and so the very last step that we're looking for is to get that ultimate approximation by plugging in the specific value we want to approximate to our line. Now that we have the equation of our line, the x value we're interested in is 97, so all other values remain the same from the slide before in terms of the slope, our a value, and our f of a value. We plug in this 97 in order to find this larger difference in x right here, and when we perform this computation, we end up with 0.0003 plus 0.01, or altogether 0.0103, as our tangent line approximation for 1 over 97. If we do remember that we have the use of technology on our hands and we pull out a calculator to compute 1 over 97, we find that the actual value is about 0.01030927. So our tangent line approximation here is really pretty darn good.